Okay, so with alkenes, what we're going to do is we're going to first compare alkanes and alkenes, because that is a very useful exercise. So we're going to compare alkanes and alkenes first. And the first thing we need to know about alkanes is that they are saturated hydrocarbons. Saturated hydrocarbons. So the word saturated means single carbon-carbon bonds, and the word hydrocarbons means contains carbon and hydrogen only. Contains carbon and hydrogen only. Okay, whereas alkenes are known as unsaturated. So they're known as unsaturated hydrocarbons. Unsaturated hydrocarbons, and the word unsaturated means that they contain carbon-carbon double bonds. Okay, now we're going to keep this comparison going, and we're going to compare in terms of the homologous series. So we've got alkanes, and we're going to look at the homologous series. Be careful with your spelling here. Remember the homologous series means this, the family of same functional group, but each member differs by CH2. Okay, and we're going to compare alkanes and alkenes. So the first member of the alkanes is methane with 1 carbon, okay, and 4 hydrogens. The second member is ethane with 2 carbons. And then you have propane with 3 carbons. Okay, so the general formula of alkanes, the general formula is CnH2n plus 2. So that's the general formula for alkanes. Now, if you look at alkenes, because you've got a carbon-carbon double bond, the first member of the family is actually ethene. So ethene, because you have a double bond, and each carbon has to have 4 lines, 4 bonds, that is your first member of your family, C2H4. And then propene is C3. So we've got 3 carbons, and you've got a double bond. Each carbon has to have 4 lines, 4 bonds, and so it's C3H6. So therefore the general formula is CmH2m is the general formula. Okay, so let's have a look specifically at alkenes now. And we're going to take butene. So if we take butene with 4 carbons, and you can have the double bond on the first carbon, or if you take butene 4 carbons, you could have the double bond on the second carbon. I'm just going to quickly fill in all the hydrogens because each carbon atom has to have 4 bonds. So I'm just going to quickly fill in all the hydrogens. Not very good writing, I'm sorry. There and there and there. These are all hydrogen atoms. There. Okay, like that. Okay, so we've got, I'm just going to put a little line between them so you can see the difference there. So the molecule on the left has a formula C4H8, okay, and the molecule on the right has C4H8 as well. So they have the same molecular formula, but the one on the left is called bute, and it's on carbon 1, so but1ene, the molecule on the left is called, and the molecule on the right, it's on carbon 2, so that is called but2ene. Okay, so they have the same molecular formula, but if we were to write the structural formula, the one on the left is CH2, CH, CH2, CH3 is the structural formula of but1ene, and the structural formula of but2ene is CH3, CH, CH, CH3. They have different structural formulas. And what's that called when you have the same molecular formula and different structural formula, it's called structural isomerism. So these are structural isomers because they have the same molecular formula but a different structural formula. Okay, let's have a look at another example. So let's have a look at, again, 4 carbon atoms. So let's draw our 4 carbon atoms. But what about this time if you've got 2 double bonds? Okay, I'm going to draw in all the hydrogens. Be very careful. Carbon has got 4 bonds. It's a very common mistake to draw the wrong number of bonds on the carbon atom. There is a double bond on carbon 1, and there's a double bond on carbon 3, sorry. So we have got bute. There's a double bond on carbon 1. There's a double bond on carbon 3. There are 2 double bonds, so we go di, and then we say diene like this, yeah? And because there's a consonant here and a consonant there, we put an A, we keep the A back in there. So buta 1,3-diene. Okay, let's have a look at the bonding in alkenes. So in alkenes, all of these lines that we're drawing here, they are called, they're covalent bonds, and they're called sigma bonds. Okay, sigma bonds. And this is where you have the overlap. Remember, the bonds are the overlap of s and p orbitals in the x and y plane. In the xy plane. Remember, an s orbital is a sphere and a p orbital is the dumbbell shape, yeah? So we have the overlap of the s and p orbitals in the xy plane. So x and then y, yeah? But carbon has got 1 outer electron in that bond, 1 outer electron in that bond, and 1 outer electron in that bond. So it's got 3 outer electrons. But carbon's got 4. Carbon should have 4 outer electrons. So there is 1 more orbital, and that's the pz orbital. Okay, so that's sticking out. So sticking out of the paper, sticking out of the board, and that's called the pz orbital. Okay, and it's sticking out, and there's 1 electron in each. And when that overlaps, the pz orbitals overlap above and below the plane. So overlapping above and below the plane, that is called a pi bond. A pi bond. A pi bond. Overlapping above and below. It's called the sideways. Quite often they call it the sideways overlap of p orbitals. But it's actually the pz sticking out. Okay, and that's the pi bond. And just one more thing to take into account when you're thinking about the shape and the bonding is that around each carbon atom there are 4 bond pairs, 4 bond pairs of electrons, but we've got a double bond, yeah, so it's like 3 bond pairs really, because the double bond has got no choice, it's going in that direction. So that shape, that bond angle, like 3 bond pairs, is going to be 120 degrees, and that's going to be your shape, trigonal planar around each carbon in the carbon-carbon double bond. All right, so let's go back to bute. Let's go to butene. All right, so I'm just going to draw carefully butene. So I'm going to draw butene very carefully, like this. Now, another thing we need to remember is that carbon-carbon double bond cannot rotate. Okay, it is fixed in position and cannot rotate. Fixed in position and cannot rotate, whereas single bonds can. When you make the models, the single bonds can rotate, and you can spin the bonds around. So we have butene, that's butene, let's just write that down, butene, but we have another form of butene. Okay, so I'm just going to draw a little line to separate them. We've got another form of butene. So if we have the H and the CH3, But what if we swap over? What about if we swap those two over? So we have the CH3 and the H. They look very similar, but they're actually, they look very similar, but they are, that's a 3 there. They're both butene. They're both butene, very similar, but they're actually different molecules, and they are isomers. They are isomers of each other. Okay, so we can see that on butene, the CH3s are on the same side as each other. So we call that the Z isomer. And on the other butene, the CH3s are on opposite sides. Okay, on opposite sides. They're on the same side, opposite sides, and we call that the E isomer. Okay, so what we've got going on here is we've got stereoisomerism. Yeah, so stereoisomers have the same structural formula. So let's just check that out. The structural formula. So for butene here, it's going to be CH3, CH, CH, CH3, and then for E-butene, it's going to be CH3, CH, CH, CH3. So there they have the same structural formula, but a different 3D spatial arrangement. Different arrangement around space. Okay, because the carbon, the CH3s are on opposite sides. And that is called stereoisomers, stereoisomerism. There are actually two types of stereoisomers. You can either have EZ isomerism, which is when you have an alkene with a carbon-carbon double bond. And there's also, in the second year of A-level chemistry, you also cover optical isomerism as well. So there's two types of stereoisomers. Okay, if we were to draw the skeletal formula, I know it's looking a little messy here, but if we were to draw the skeletal formula, you would just simply draw this like that, and the skeletal formula of this one would be like that. The skeletal formula. Okay, let's look at this stereoisomerism in a little bit more detail. So let's take a more complex molecule. So we're going to take this alkene, just going to carefully draw it up, and we've got a, let's put a CH3, and let's put a CH3 here as well, and let's put a chlorine here. Okay, now for more complex molecules, it is difficult to assign whether they are whether they're E or whether they're Z. All I'm going to do is swap around on the right hand side here. Just swap around on the right hand side. Let me tidy that up a little bit. There we go. Okay, now there's something called Cahn-Ingold Prelog rules for naming EZ isomers. They're called the CIP rules. The CIP rules, okay? And this gives atoms priority. Okay, and the highest priority goes to the atom with the highest priority. The highest priority, pardon me, is the atom with the largest atomic number, with the highest atomic number. So the highest priority goes to the atom with the highest atomic number. So let's have a look on the left. Let's have a look at chlorine, and let's have a look at carbon. So it's the atom that's joined to the carbon of the carbon double bond. Which one has got the highest atomic number? Well, it's the chlorine, isn't it? So we give that the highest priority. So we say that that is the highest priority. Then we do the same thing on the left hand side, and we go carbon, and we say hydrogen. Which one has got the highest atomic number? And again, it's the carbon. And the two with the highest atomic number are on the same side of the double bond, and it's called the Z isomer. let's do the same thing with the with its other isomer. So we say which one has got the highest priority? It's the Cl. Which one on this carbon on the right hand side has got the highest priority? It's the carbon, and they are on opposite sides, and that is called the E isomer. Okay, now just to complicate things, make things a little more complicated, we've also got something called Cis Trans Isomerism. So Cis Trans Isomers is a special type. It's a special type of EZ, yeah? Special type of EZ isomerism. A special type of EZ isomers. Okay, now it's special because you have to have the same group. You have to have the same group on each carbon in the carbon-carbon double bond. In the carbon-carbon double bond, you have to have the same group in each carbon of the carbon-carbon double bond. Now, this is looking a little messy, so what I'm going to do is I'm just going to tidy it up a little bit, and then I can show you. Let's redraw it. It might be quicker to redraw it than tidy it up. So let's have a let's draw that molecule again really quickly. Just the same. I'm just drawing just the same molecule. We've got that one, which we said was the Z isomer. Okay, we said the Z isomer because that and that are the highest priority, and they're on the same side. And let's draw the other isomer where we've swapped over. The left-hand side is the same, but all we've done is swapped over the right-hand side, and we said that that's the highest priority, that's the highest priority, and we call this the E isomer. Now with cis trans, I'm going to use the blue colour. Cis trans, we have a CH3 group and a CH3 group, and they are the same group on each carbon of the carbon-carbon double bond. And because they are opposite each other, we call that the trans isomer. And here, because the CH3s are on the same side as each other, we call that the cis isomer. So cis and trans is just a special type of EZ, and you actually have to have the same group on each carbon of the carbon-carbon double bond. Let's do one more example. I know we've been doing a lot of examples, but let's do another example, slightly more complicated. So let's draw it out because it is a bit more complicated. We've got an ethyl group there, and we've got a methyl group here. And then we've got a methyl group on that side, and we've got a hydrogen there. Okay? That's a methyl. Be careful with your connectivity, yeah? So let's assign priority. Carbon has got a higher atomic number than hydrogen, so that's got the highest priority. Okay, but on the right hand side it's a bit more complicated because we've got two carbons attached, so therefore we have to go to the next atom, and the next atom is a carbon and a hydrogen, so therefore the carbon has the highest atomic number, so we would give the ethyl group the highest priority. The highest priorities are on the same side, and that would be called the Z isomer. In terms of cis and trans, the CH3 and the CH3 are on opposite sides, so that would be called the trans isomer. Okay, right, one final job just to finish us off here. If you were asked for the to draw the structural isomers of C5H10, draw the structural isomers of C5H10, you would keep your answer very, very organized. Okay, I'm not going to draw the hydrogens because I haven't got much room, so I'm just going to draw the carbon skeleton like that. So we have got pent 1-ene because the double bond is on the first carbon. Then if we had 5 in a row again, but we put the carbon-carbon double bond on the second carbon, then that would be called pent 2-ene. Now there aren't any more now for 5 in a row, so let's go to 4 in a row. Let's again put the double bond on the first carbon, and let's put the methyl there as well. So that would be bute, 4 carbons, the double bond is on the first carbon, the methyl is on the second carbon. So I've got 1, 2 like that, and 2 methyl bute, 1ene. Then 4 in a row. Let's keep the double bond on the first carbon and let's put the methyl on the next carbon. So again, that'll be bute, 1ene, but now the carbon is on, the methyl is on carbon 3. So we'd call it 3 methyl bute 1ene. And then finally, yeah, so we've got 4 in a row. We put the double bond on carbon 2 and we put the methyl on carbon 2. So we'd have bute 2ene and we'd have 2 methyl. So there's 5 isomers of C5H10, and they had the same molecular formula, different structural formula. Okay, now which ones are stereoisomers though? Okay, so they're structural isomers, but which ones have stereoisomers? Which ones have stereoisomers? Now, in order to have stereoisomers, you have to have a carbon-carbon double bond because it cannot rotate, and you have to have 2 different groups on each carbon. On each carbon of the carbon-carbon double bond, you have to have 2 different groups. So we're going to take this very first example, pent 1ene. Okay, I'm just going to draw it clearer. 1, 2, 3, 4, 5, pent 1ene. Does it have a carbon-carbon double bond? Yes, it does have a carbon-carbon double bond. Does it have 2 different groups? So 2 different groups on each carbon of the carbon-carbon double bond. 2 different groups on each carbon of the carbon-carbon double bond. Okay, no, because there's a H and a H. They're the same thing. If we swap them over, okay, let's watch this. Let's quickly swap them over. So H, all the rest of the H's on. Okay, and we swap them over. Are you ready? We're going to swap over these H's. We're going to swap them over. Oh, right. So it's exactly the same molecule. So it doesn't have 2 different groups on each carbon of the carbon double bond. So that first molecule, does not have stereoisomerism. Okay? The second one does, because the second one has got a CH3 and a H, and it's got a H and a CH2. So that does have stereoisomers. The third one here does not have stereoisomers because it's got 2 H's. This one, 3-methyl bute 1ene, doesn't because it has 2 H's on the carbon, and the last one doesn't have stereoisomers as well. So the only one that has stereoisomers is pent 2ene. So pent 2ene has got stereoisomers because it has got, let's just quickly draw that up, CH2, 1, 2, 3, 4, CH3, H. It's got that isomer and it's got the, swap those over, bring it down there. 1, 2, 3, 4, 5. We have got the that is the Z isomer, and this one here is the E isomer on the opposite side, and then the cis trans. The H's are on the same side, so that would be called cis. The H's are on opposite sides, and that will be called trans.